Hi everyone, today we're going to study real numbers and its subsets. For today we're going to consider some groups of numbers such as natural numbers, whole numbers, integers, rational numbers, irrational numbers, and real numbers. The first group is what we call natural numbers, or sometimes called counting numbers. This is denoted by capital N. The set of counting numbers starts with 1, 2, 3, so on and so forth. If we're going to count the number of birds in our screen, we will count it from 1, 2, 3, and we say there are 3 birds on screen. The next group is what we call whole numbers, denoted by this capital W. This time we're going to include the 0 plus the counting numbers, and it is called now whole numbers. So the set W is equal to, starts from 0, 1, 2, 3, 4, so on and so forth, as it is shown in our number line below. The next group is now called integers, denoted by Z. For integers, we are now including the negative numbers plus the whole numbers. The set Z is equal to ... The negative numbers here, the 0 is here, the positive numbers are here. As you see in the number line below, 0 is in the middle. All numbers on the right are positive numbers. All numbers to the left are negatives. The integers include the 0, the counting numbers, and the negative of the counting numbers. The next group is rational numbers, denoted by Q. This time we have 3 cases for a rational number. The case 1 is a rational number can be written as a ratio of 2 integers with non-zero denominator. It means it is denoted by P over Q, where P and Q are integers, and of course the Q cannot be equal to 0. Examples are the numbers 2, -5, 11, 0, 2 over 3, this is a fraction. Square root of 4 can be simplified into a positive 2, and other rational numbers. So these are the examples for this case 1, and this falls under rational numbers. For case 2, when we have a decimal expression, a decimal is called a rational number if it is terminating. Look at the examples: 1.25, 3.562, -0.75, -6.4563. So these are decimals that are terminating, and they are called rational numbers. For case 3, again this is for decimal expression. If the decimal is non-terminating and repeating. Look at the examples below. 2.333 and 3 dots follows. It means, as you see here, 2.333, there is a pattern of repetition of the number 3, And see the 3 dots here means it is continuously. It is continuous. The third case is about decimal expression also, but this time the decimal is non-terminating but repeating. Look at our examples below. The numbers 2.333 and there are 3 dots that follow here. It means it is continuous. But because of this pattern of repetition of 333, this is considered to be a rational number. Look at the second example here. There are 3 dots at the end of the decimal. It means this is non-terminating. But because of the pattern of 232323 after the decimal point, it means there is a pattern of repetition here. So this is a rational number. Look at the third example, negative 12.543, and ... Because of the repetition pattern of 543 and followed by another 543, we can see the pattern of repetition here, and this is not terminating. It means this is called also a rational number. How are we going to determine if this is not a rational number? Let's see the example in number 2. The example 2.34532, there are 3 dots that follow. It means this is continuous. But the decimal itself, there is no way that we can see a pattern here, unlike what we have in our example 1. So this is 2.34532 ... There is no pattern of repetition, and this is continuous. It means this example is not a rational number. Another example is negative 0.23125 ... It is non-terminating, but there is no pattern of repetition of the decimal, so this is a not rational number. Another example is here, 125.34526 ... So this is continuous, and also there is no pattern of repetition, so this is an example of not rational number. The next group is what we call irrational numbers, denoted by capital I. So when a number is not rational, it is called irrational numbers. So we have some examples here. The numbers square root of 2, square root of 3, square root of 5, these are irrational numbers. If you're going to get the exact value of this square root of 2, square root of 3, square root of 5, you will get a decimal that is non-terminating and not repeating. Another examples of irrational numbers are the pi, which we know the value is 3.14151 ... Also this e, this is a special number that is studied when you reach your higher math, and the value of this e is 2.71828 ... So these two special numbers here are called irrational numbers. Another example, 1.235241 ... It's continuous and there's no pattern of repetition. This is an irrational number. Another example, negative 5.24158. 3 dots follow. There is no pattern of repetition in the decimal, and it is continuous. So this is an example of irrational numbers. So this just to remind us that when we use the symbol square root, we will always use the positive number. So the example here, the square root of 4 will give us 2, positive, even though we know that both 2 and minus 2 or negative 2 are considered correct answer for the square root of 4. So when we have the square root of 4, we will take only the positive 2 as the final answer. The last group is what we call real numbers, as denoted by R. So all the numbers that we studied, when we combine the rational and irrational numbers, all of them are inside the real numbers. All of these numbers, all numbers of all rational or irrational numbers are called so for the last group is what we call real numbers, and this includes the set of rational numbers and also the set of irrational numbers. As you see in the equation here, the capital R equals, it is small x such that the x is a rational or irrational number. As you see in the number line, all of these numbers here in the number line is called rational numbers. As you see here in the number line, all of these numbers are called real numbers. For illustration, we will have the subsets of real numbers. As you see here, there is a big rectangle here, and this big rectangle is divided into two. On the left side is a yellow colored, the right side is gray colored. On this left side, there is an inner oblong here that is about the natural numbers, and these natural numbers is inside the bigger oblong that is a whole numbers, and these two groups, the natural numbers and the whole numbers, are inside a bigger group, and that is the integers, and these integers are inside the rational numbers, the yellow color, and there is an irrational numbers on the other side. It means for the rational numbers and irrational numbers, they are called mutually exclusive. There is no common numbers between rational numbers and irrational numbers. If we're going to combine now the rational numbers and the irrational numbers, this is now what we call the big group of real numbers. So if we're going to use symbols, so the n, the natural numbers are subset of whole numbers. The whole numbers is a subset of integers. Integers is a subset of rational numbers. Rational numbers is a subset of real numbers, and the irrational numbers are also a subset of real numbers. So the real numbers is the biggest group for all these sets of numbers. So this exercise, we have some numbers written here. So let's start. It says here we're going to complete the table, and we're going to tick if the given example falls on that subset or group of numbers. So for number 10, it is a natural number, it is a whole number, it is an integer, it is a rational number, and tick the real number. For the pi, it is an irrational and also real. For the 1/4, it is a fraction. This is a rational number and also real number. For 0, it starts with the whole number, it is integer, it is rational, it is real number. The cube root of 5, it is an irrational and real. For 0.768, this is a decimal, it is a rational number, it is real number. For the number 5.23654, ... it is a continuous decimal. There is no pattern of repetition of the decimals. So this is irrational and real. Thank you for watching the video. See you in the next video.